let's skip to slide 16, which is, you can find it in the slide deck or on page 57, figure 310 in your textbook. And what we have here is a really good example of what's called a Mach Band. Usually whenever you see this shadow being cast on a lighter surface, we almost always perceive this weird fuzzy light band running next to it. Now there's the dark from the shadow, and then there's the light that's bouncing off the paper in the back. But right at the border, we always perceive a fuzzy band. Okay, actually, that fuzzy band is not there. If we were able to look at this through some other way or perceiving it, for example, to put photo detectors here, a whole bunch of photo detectors, we would not have a fuzzy band. It would be very clearly dark and light. This fuzzy band is a result of the way our retinas are wired due to lateral inhibition. Okay, the receptors that are being stimulated by these spots here, the dark spots, they are not inhibiting each other very much at all. Right, so these where these dots are falling on your retina, they're not being inhibited very much because they're not being lit up at all. Right, they're not being lit up at all. These receptors here, wherever this falls, these spots, for example, fall on your retina, are being activated quite a bit. They're lighting up. And also they are inhibiting their neighbors a little bit, right? Because they're inhibiting each other, right? But since they're being lit up, the inhibition, this inhibition that happens between these different receptor areas isn't having that much of an effect, except right here, okay? You have to remember these guys here on the border, they're not being lit up, right? They're in the dark. However, no, I'm sorry, let me back up. These guys on the border here are being lit up, right? They are being lit up, but they are also being inhibited by the dark areas, okay? So these guys right here, the ones that are in the outside, in the light band or in the dark band, they're either not being lit up, not being activated, or being activated, and the inhibition is not that significant because the inhibition doesn't make much difference here because these guys are lit up, and it doesn't make much difference here because these guys are not lit up. So the inhibition is not going to have that much of an effect. Where it does have an effect is right on the border, right? On these receptive areas that, wherever this is landing on the retina, right? These receptive areas here are surrounded on one side by a dark band and one side by a light band. Okay, and as a result, they are going to be they want to be light, right? But they're being inhibited by the dark band, right? So they are a little bit less light than the guys that are in the light band. Okay, and this is all due to lateral inhibition. Okay. So all the receptors are receiving lateral inhibition from neighbors. Now in the low and high intensity areas, the amount of inhibition is equal for all the receptors, right? So if you're a receptor in the dark area or if you're a receptor in the light area, the amount of inhibition is the same, right? It's the same. So it doesn't really affect your glow, the way you're glowing relative to, or the way you're firing relative to your neighbors. However, the receptors on the border receive different inhibition, right? This is illustrated, let's see. Let me see if I can find that. Well, if you look at figure 311 on the bottom of page 57 in your textbook, you'll see this really great diagram of receptors that are actually that, and I forgot to turn my timer on. That was just really smart. Hang on a sec. So you'll see some receptors here on this figure, on figure 311 in your book, right, that are in high intensity area and low intensity area. You'll notice that the ones in the high intensity area where the light is, right, are shooting out at 80, over 80 units, right, of activation. The ones in the low intensity area are only shooting out 16 units. But you'll also notice that right there in the middle, right there in the middle, there are two sides, right? The ones in the high intensity area, remember, they're in the high intensity area, so they are actually right. It's the ones on the border here. Whoops, I did it again. It's the ones on the border here, right? They are not getting inhibited by these guys. Okay, so you have this lighter band here. Right, you have a lighter band here because they're able, the receptors that are receiving this information right here. So here's the border, right? We'll call this the border. Oops, let me get my pen going again. Pen, right? So here's the border right here. We'll say this is the border. Yeah, we'll say this is the border here, right? There's the border, right? So the neurons, the cones that are getting stimulated by the information coming from here, right? They are not getting inhibited from this side, right? There's no inhibition coming from here. These guys here, they're getting inhibited from all sides, right? However, these guys are getting inhibited from here and from here and from here, but they're not getting inhibited from here because it's dark. What that means is that they're going to be a little bit brighter, as you can see in figure 311. The receptors that are right at the edge on the high intensity side are firing at 88, which is 8 units higher than the ones that are sitting here, right? So you're going to have a light band, right, because it's firing a little stronger. And then you're going to have a dark band. Right? You're going to have this dark band here, and the reason you have a dark band is because not only are the receptors that are receiving this area not firing very much at all, but they're being inhibited. Who are they being inhibited by? These guys right here. Right? These guys right here. Whoever's next door to the light band, he's not getting inhibited from here. He's not getting inhibited from here, and he's not getting inhibited here, but he is getting inhibited from here. So he's going to be darker than his neighbors, than his other neighbors in the dark side, right? And that accounts for the light band and the dark band, right? So on the low intensity side, where it's dark, there's additional inhibition resulting in an enhanced dark band, right? So that additional inhibition is because of the fact that it's sitting next to the light, and the light receptor is receiving the light, firing off, and it's also inhibiting its neighbors, including that one set of receptors that lies along the edge of the dark band. On the high intensity side, where the light is, there's less inhibition. Right? So there's not that much inhibition on the cells that are sitting right next to the dark band, right? Because they're only getting inhibited on 3 sides. The side that's facing the dark, they're not getting inhibited. Why do we do this? Right? So why do we have lateral inhibition? Right? You have to ask yourself. We have this mechanism for lateral inhibition where a receptor lights up and it inhibits the firing of its neighbors. You have to ask yourself, why do we have that? Well, it helps us to find edges. It helps us to find contours, right? If you think about it, if you look back at the Mach, right, what it's doing, I mean, what this is allowing us to do is to more clearly identify and find this edge, right? Because it puts a light band and a dark band, and it clearly defines where that edge is. Okay, so the purpose of lateral inhibition is a first level analysis on detecting contours and shapes detecting borders where one shape begins and another shape ends. Okay, that's the purpose of it. Right. Here's another example, right? So if you look at this series of squares, or I'm sorry, rectangles going from light gray to dark gray, and you pick 4 points on this rectangle: point A, point B, point C, and point D. Right? Physically, right? Physically, this is what the intensity is, right? Physically. So A and B are the equal brightness, and then the brightness goes down for C and D. Okay, and there's no, there's no dip or anything. It just automatically goes down. However, and that's the physical light intensity. So if we were to measure the light that's bouncing off of these areas, we would get different measurements. However, our perception of that light is different. It's not this, right? It's this, where the borders, so B and C are the border spots, right? So B is next to the dark border and C is next to the lighter border, right? The borders are going to represent a light band on the B side and then a darker band on the D side, okay? And again, the reason that lighter band is there, right? The reason the B spot is glowing brighter than the A spot is because it's not being inhibited as much because it's over here next to the C spot, which is darker. Since it's darker, it's not putting out as much output, so it doesn't have as much output with which to inhibit. Okay, and then the reason we have the dark spot in C, right, is because it's dark. It's darker, right? It is darker than this guy here, and it's dark like its neighbors, but it's next to a brighter spot. And what do brighter spots do? They inhibit. They inhibit their neighbors. Right? So B is going to be inhibiting C. C is not going to be inhibiting B, and as a result, you're going to have a bright spot here and a darker spot there, and that is the Mach effect. Okay. Let's see. This is actually a cartoon drawing of how shall we say, data that comes from the firing of cells, right? We're actually looking at cells on different points on that, like the ones that we saw here, right? We're looking at cells A, B, C, and D, right? So there's A, B, C, and D. And you'll notice that cell B, which is the one that's in the light spot near the border, right, is firing pretty high. Again, that's because it's not being inhibited by C. It's being inhibited by everybody around it, but it's not being inhibited by C because C's dark. So it gets to fire a little bit more because it's not being inhibited as much as this guy or this guy. This guy here fires less than his friends, than 16 and then D and Y. And the reason he fires less is because he's being inhibited by some light-colored guy over here, right? So he gets inhibited more than these guys who only have dark areas around them, right? But this guy is next door to the brighter area, so as a result, he gets a little bit of inhibition. So he's going to look a little bit darker than his neighbors. Okay. So people see this illusion of changed brightness or color due to the effect of the adjacent area. So the area next to something is going to change the way we perceive it. Okay. And this general rule applies, right? An area that is the same physical intensity, right? So it's all the same physical intensity. It's lighter when it's surrounded by a dark area and darker when surrounded by a light area. Okay? So basically, we have this perceptual trick that is played on us because of lateral inhibition, right? Where if you were to take a black piece of construction paper and then put a gray square, you would end up with the gray square actually looking lighter. It would actually look lighter than it did if you were just looking at it by itself. Okay. The receptors that are stimulated by bright surrounding areas send a large amount of inhibition to cells in the center, right? So if there's a receptor sitting there, right, and it's being there's a lot of light hitting that little receptor, right? It's going to be sending a big signal out that it's because it's being stimulated, but it's also going to be sending out a lot of inhibition to all of its neighbors, right? As a result, the perception is of a darker area than when the stimulus is viewed by itself, right? So you have a little bit of a darker area in that spot because this guy is inhibiting everybody else, right? The receptors that are stimulated by by a dark surrounding area send a very small amount of inhibition to the center, right? So if I had this area, right, if I had this area that was all dark, right, and then here in the middle there's a receptor, right? So imagine I have the area in the dark, and in the middle there's a receptor, right? That receptor in the middle, if it's surrounded by dark, is not going to be inhibited that much, right? Because it's surrounded by dark. And if I shine a little bitty light in there and don't shine any light in the outer area, right, it will not be inhibited. So it's just like this, right? So the receptor, right? So if I draw it down here, right, this receptor is here. Whoops. Oh crap! I always do that, don't I? So let's see. There's my pen. So this receptor sitting here, around this spot right here, right? And if it is sitting, in a circle that's all dark, so let's say this circle's all dark, right? Let's say it's all dark. Well, since it's all dark, right? Since it's all dark, if I were to shine a little tiny light right here on top of this receptor and no light anywhere here in this area, this receptor would fire very powerfully, right? Because it's not being inhibited by any of the guys out here, right? It's not being inhibited, okay? So what we would see is, what we would perceive is that this little spot right here would be much brighter than the stimulus actually is, right? We would perceive this light spot as being much brighter than the stimulus is, simply because it's not being inhibited as much, okay? Now, if you look at this illusion is on page 58 of your book, right? This is a very interesting illusion with showing simultaneous squares, right? And the squares look different, right? The square on the left looks like it's darker than the square on the right, which looks lighter. But in fact, they are both exactly the same shade of gray. Exactly the same shade of gray.